Welcome to this video. In this video we will be talking about polynomial curve fitting, so that by the end of this video you will be able to find polynomial functions that best fit a given data set. Now, polynomials are just a special type of nonlinear functions that have the following form. Some f of x, which is the polynomial, is a constant a0 plus another constant a1 times x plus a third constant a2 times x squared, and so on, all the way for an nth order polynomial plus a sub m times x to the power m, where x can be any real number and m can be any whole integer number greater or equal to 0. Now, a set of n data points can be fit by a polynomial of degree m smaller or equal to n minus 1. And here are some examples of this. So, for example, we have the shown blue data points here, and if we wanted to fit a degree 1 polynomial to this data, we would do linear regression that we covered earlier, and the shown black line would be a first degree polynomial fit. But we can fit higher degree polynomials as well to this data, and here's an example of a second degree polynomial fitted to a total of 11 data points. This is an example that we would get if we would fit a third degree polynomial. Here you'll see a fourth degree polynomial, a sixth degree polynomial, and we can go all the way for 11 data points to a 10th degree polynomial, which is a special case for 11 data points, because in this case, the 10th degree polynomial will go exactly through the data points. So therefore, that would be interpolation, really, instead of curve fitting. Now, when we have n data points, we can go up to an n minus 1 degree polynomial. But which degree polynomial should we choose? Well, in general, the higher the order, the closer the fit passes by the data points. Remember, for a curve fitting approach, the curved fit data, the best fit polynomial, does not have to go exactly through the data points. It just has to fit the data points in the best possible way, minimizing the overall error. Now, if the polynomial is of order n minus 1, then the polynomial will pass through the data points exactly. And here are some of these examples that we have seen before, with a 10th degree polynomial passing through the data points exactly. But you'll also notice in this 10th degree polynomial that the higher the order, in this case 10 here, the greater the likelihood is that the data between points is not very well represented. So it's very unlikely that near the end points here of the data set, there are these vast overshoots actually present in the data, which the polynomial predicts. So here's a rule of thumb. If the data points have large error, which can be, for example, from measurement uncertainty and experimental, when you use an experiment to get the data, then you would choose a lower order fit for the lower order degree for the polynomial. But if, on the other hand, the data points are very precise, you can choose a higher order polynomial to fit the data. Now, the purpose of polynomial curve fitting is to find the coefficients a sub I in the form shown here for an nth degree polynomial. So how do we do this? Well, similar to linear regression, we will do polynomial regression, in the end following the exact same steps as we did for linear regression, realizing that linear regression is just polynomial regression for an order 1 polynomial. So let me write the polynomial in this short compact form, that f of x is equal to the sum of a sub I times x to the power I, where I now goes from 0 to m for an nth degree polynomial. And if I have n data points that this polynomial is supposed to fit, I can plug in my data point values x1, x2, all the way through xn into this polynomial form. And this is just written here in the form of a matrix times the vector of the as of yet unknown coefficients a sub I. And this matrix X times the vector A is then equal to f of x, which is supposed to be as close as possible to the vector of measurement values y. Okay, so now let's define the total error, as we did before, as the sum of the squares of the residual values. So that's what's written here, right? We have n total data points, so we take the sum from k equal to 1 to n of the residual, which is the measured value y sub k minus the polynomial regression predicted value f of xk. We square that and sum these all up. Okay, so let me rewrite this a little bit. The first part I just leave as is. And for the second part, I'm going to plug in the definition of the polynomial. So f of xk is just the sum from I equal to 0 to m of a sub I times x to the power I. And then I'm going to square this. Okay, so now this is really the residual for each one of my data points squared and summed. So if you think about the residual as a vector, right? Every entry in that vector is the residual value for each one of the data points. Then this is just the definition of what the length of this vector squared is. So let me write the error then, excuse me, in the following way. As the length of this vector r squared. If you recall from linear algebra, how do I calculate the length of a vector squared? I'm taking the transpose of that vector times the vector itself. So this would be y minus x times a transpose times y vector minus x times a. Let's multiply this out. So I get y transpose times y. Then I have minus y transpose times xa. And now minus a transpose x transpose times y. And then finally we have plus a transpose x transpose times x times a. Now, this is the definition of the error, and we want to find the polynomial that best fits this data, meaning that minimizes the error. So we need to find the position where this error is minimum. And the way we do this is we take the partial derivative of the definition of this error with respect to every entry of the vector a that contains the coefficients of the polynomial. So let's take this derivative. The first term y transpose y is not a function of a, so that the partial derivative is 0. And then these next two terms, if we take the partial derivative with respect to the a vector, we get minus x transpose times y, and again minus x transpose times y. And then finally we have to take the partial derivative of this last term with respect to the vector a, and that yields 2 times x transpose times x times the vector of unknown coefficients a. Now that we want now to set equal to 0, because that will define the location of a maximum or a minimum, and in our case it will be a minimum of this function. Okay, so let's solve this. So we have 2 times x transpose x times a. Let me just divide by 2. That gives me on this side x transpose times x times the vector a is equal to, we have negative x transpose times y 2 times there, so divide it by 2 and move it over to the other side. That gives me x transpose times the vector of measured values, y. So that's the equation now that we would need to solve to find our optimum coefficients for the polynomial a. So this is now the procedure for the mth order polynomial fit to n data points. The first step is to calculate the n by m plus 1 matrix x. And this is basically just each one of the measured values, x1, x2, x3, all the way to xn, taken to the power 0, 1, 2, all the way to the power m. Each row is for one measured data point, and then the columns are just increasing powers of that x value, starting with the 0th power all the way to the mth power. And if we write this in index form, that just means that the ij entry of this vector, of this matrix x, is just x sub I, where I is the number, the measurement point number. So x sub I to the power and j minus 1, where j is the column number. And then we have the vector y, right? That contains from the data pair, the other part of the measured data set. We have n of those y values. So with x and y defined, what we can then do is calculate x transpose times x and x transpose times y, which then results in a system of linear equations, a times the vector of unknown coefficients a times the right-hand side vector b, that we then need to solve. And if we do this numerically, we're going to use our Mygos-Jordan algorithm that we developed earlier in the semester. Okay, so let's do an example for this. And the example is find the quadratic polynomial best fit to the following data set here. There's some x values and some y values. And if I would fit this data, well, you see first here these black dots here. That is the data set itself. And now let's try to find this polynomial that best fits this data set. And I'm just following the steps that I just outlined before. So let's start out with, how many data points do I have? That's my n, right? This was 1, 2, 3, 4. There's n equal to 4 data points. And what's my m? My m is the degree of the polynomial, and that's given here in the problem statement. In an example, I want to fit a quadratic polynomial so that m is equal to 2. So the first step then was find that matrix x, okay, and x was just, let me just write this here again. It is a matrix where I take the first data value here, this 2, and I'm going to take it 2 to the power 0, 2 to the power 1, 2 to the power 2, and I have to go all the way to m, which is 2, so all the way to 2 to the power 2. Next up is the second data value, so that would be 5 to the power 0, 5 to the power 1, 5 to the power 2. And then I move to the third data point, 6 to the power 0, 6 to the power 1, 6 to the power 2. And then finally the last data point, 8 to the power 0, 8 to the power 1, 8 to the power 2. Okay, let's calculate this. So this would be 1, 2, and 4. 1, 5, and 25. 1, 6, and 36. And then finally 1, 8, and 64. So that's my matrix X. And then I need to calculate X transpose times X and X transpose times Y. So let's start with X transpose times X. That's equal to, here's the matrix of X. So that is 1, 1, 1, 1, 2, 5, 6, 8. Right, all I'm doing is here's my matrix X, and I'm just writing it in the transposed form. Then the last row is 4, 25, 36, and 64. And that now multiplies the original x, which was 1, 1, 1, 1, 2, 5, 6, 8, 4, 25, 36, and 64. Okay, so we'll have to multiply this together. So 1 plus 1 plus 1 plus 1 is 4. Then we have these ones here times 2, 5, 6, 8. So we need to sum those values. 2 plus 5 is 7, 13, 21. Okay. And then we have to do 1 times 4 plus 1 times 25 plus 1 times 36 plus 1 times 64. So that's 100. That's 129. Okay, now, if you remember from linear algebra, what happens if you take a matrix and multiply it by its transpose? The result will be a symmetric matrix. So then I already know what the entry is going to be right here and here, because the resulting matrix here will be symmetric. So this will have to be a 21 and a 129. And now I'll have to multiply 2568 times 2568 and sum that up. That will give me, again, 129. And then I'm going to multiply 2568 with 425, 36, 64. If we do this, that gives us 161. And because of symmetry, this has to be 161 as well. And then finally, we have 4 times 4 plus 25 times 25 plus 36 times 36 plus 64 times 64. And I have to read off that result. That is 6,033. So that's x transpose times x. And now I need to calculate x transpose times y. Okay, so that's my x transpose again. 1, 1, 1, 1, 2, 5, 6, 8, 4, 25, 36, 64 times the vector of y values. Right, those are these here. 7, 8, 10, and 11. 7, 8, 10, and 11. And if you multiply this out, you will get a vector that is 36, 202, and 1292. So that's my vector B. This here I will call A, my matrix A. And then the next step is we need to solve the matrix A times the vector of the as of yet unknown coefficients. A, little a, is equal to B. So we're going to use, for example, Gauss-Jordan with partial pivoting, of course. Pivoting to minimize the impact of round-off errors. And if we do this, the answer would be the vector of A values, which is like A sub naught, A sub 1, A sub 2. That would be equal to 6.32 and so on, further digits, 0.2033 and further digits, and 0.05 and further digits. So those are the coefficients. So now I can write that best fit quadratic polynomial. So f of x is equal to a naught plus a1x plus a2x squared, and that's equal to 6.32 and so on, plus 0.2033 further digits times x, plus 0.05 further digits times x squared. And this is now the best fit quadratic polynomial to this data set. Okay, let's look what this actually looks like. Let's go back here. All right, that's the, these are the values that we just determined. And that best fit quadratic polynomial is shown here in red as a red line. And it seems to fit that data pretty well, right? It's of course not an interpolation, so that curve does not go through each one of those data points. But it is, well, it is the best fit quadratic polynomial to this data. Okay, so now what order polynomial should you choose? Basically, what is the m supposed to be? Now, typically in engineering applications, the order of the polynomial is given by the physics of the problem itself, basically the underlying model that you're trying to fit. So here's an example of 100 measured positions of an object. Right, and obviously I'm not that good at measuring data, so there's quite a bit of scatter in this data, so in time and the position that was measured of this object. And for the model, let's assume that the object has a constant acceleration, meaning the force acting on that object is constant. So then physics tells us that the position is equal to 1/2 times the acceleration times time squared, plus the initial velocity v naught times time, plus the initial position s naught. So I got these 100 measured data points for the position as a function of time. And I know that my model that describes the position is a second degree, a degree 2 polynomial. So let me fit a second order polynomial to this data, right? That would be s equal to a0 plus a1t plus a2t squared. Okay, so if I have this data set and I go through the process that we just did on paper, just with a different data set and a larger data set, I get the following values for a0, a1, and a2. So I can plot this quadratic function now, and that's shown here in red. That's the quadratic polynomial that best fits the measured position data. And I can now calculate what the acceleration of this object is, right? Because the prefactor, the a2 that multiplies t squared, is equal to 1/2 times the acceleration, which means the acceleration is 2 times my a2. And in this case, the acceleration would be 0.39764 in dimensionless units. We can also determine what is the initial velocity of the object. That's the prefactor a1. In this example, the initial velocity would be negative 1.0276 in non-dimensional units. Thank you for watching.